Welcome to Organic Chemistry. In this unit, we will focus on alkynes and acetylides, their stability, nomenclature, and reactions. Let's get started. Alkanes are formed of carbons that are sp3 hybridized. Their bond strengths are not as strong as alkenes and alkynes, which have different hybridization. Alkenes with higher S character, sp2 hybridized orbitals, have stronger bonds. It is important to note that the double bond is form of a stronger sigma bond, but a weaker pi bond, which we emphasized in terms of its reactivity. Alkynes are associated with the strongest bond, the triple bond, due to the sp hybridized orbitals and, of course, the multiple bonding between the two carbon atoms. Our IUPAC nomenclature will follow the rules previously discussed in class. Here we now provide the ordering for the first 20 functional groups. There are other minor groups that we could include here, but these are perhaps the most prominent. And alkenes are definitely higher in priority than alkynes, which are higher in priority than halides. For reactions with alkynes, we start with the addition of HBr. Alkynes can add HBr, but notice the clear difference. These are slower than alkenes. They form a vinyl carbocation, an sp2 hybridized carbocation. And clearly, that carbocation cannot rearrange because rearranging would destroy the pi bond stabilization. So HBr addition becomes regioselective but rigid. And the second equivalent always binds onto the same carbon atom. And this gives us geminal. Gemini means twins, geminal dihalides. Now, let's continue on to halogenation and halohydrons, what we previously encountered with alkenes. And they work beautifully with alkenes. Technically, they can happen with alkynes, but they require bromonium ion intermediates. These are rigid, sigma bridged. They require two strong sigma bonds, and they force the geometry on to the cations. Remember, sp2 hybridized means that our ideal geometry is 120 degrees in bond angles. Alkynes cannot support that geometry. The result is massive instability, and we have no kinetic control. So, in practice, we do not use halogenation or halohydron chemistry on alkynes. And what if we try acid and water alone on an alkyne? Oh boy. You will form a vinyl carbocation, which is not stabilized, and it attacks other alkynes, and it makes a polymer tar. It destroys our molecule faster than it functionalizes it. Now we introduce Hg2 plus, and everything changes. Mercury does not force sigma bridges. It forms soft pi complexes. It polarizes the alkyne. It lowers its energy, creates a controlled field, and allows a clean water addition. You get only ketones, no rearrangements, clean regioselectivity. Of course, the keto enol and tautomerization locks the carbonyl into place. Now let's flip the polarity, just like we did with alkenes. Dicyamylborane. It's bulky and gentle. It adds from the less substituted end, and oxidation converts the enol to a carbonyl. Terminal alkynes become aldehydes, and internal alkynes become ketones. Birch reduction. This is the process of making transalkenes from alkynes. We begin with solvated electrons attacking the pi system. Only internal alkynes can stabilize the radical intermediates. So, in this example, internal alkynes yield transalkenes, but clearly terminal alkynes yield acetylide anions. Here, hyperconjugation determines what endures. But now we can make terminal alkynes with sodium amide. The strong base does two eliminations on the dihalides provided. We can do this on vicinal dihalides or geminal dihalides, it doesn't matter, as long as they are either primary or secondary to the terminus. And we can turn those acetylide anions into incredible tools. Terminal alkynes can be deprotonated into these acetylide nucleophiles. They perform excellent SN2 reactions. They can attack epoxides, and they can build carbon chains. Hydrogenation with alkenes produced alkanes with rainy nickel or palladium with carbon and with platinum. With alkynes, we get the same result of alkanes, which is not preferred. We want some other possibility. And so we have the option of poisoning the palladium. In this example, then, only alkynes can bind to the palladium, and alkenes are too bulky. So hydrogen can only add once, and we produce the cis-alkene, which is in contrast to the trans-alkene we've previously discussed in production. And with this, the reaction stops. Clearly, the takeaway is alkynes don't tolerate a enforced structure. They respond to fields, not cages. Till next time, Crip.